Now that we've learned how to evaluate logarithms and to graph logarithms, we're going to learn a couple of rules to be able to rewrite a logarithm. So there are 3 laws of logarithms, as we call them, and they tell us how to rewrite a logarithm that might have maybe a complicated argument. If the argument of a logarithm has multiplication, division, or exponentiation, we can use laws of logarithms to rewrite them. If the argument of a logarithm has the operation of multiplication on the inside, we can rewrite it as addition of 2 different logarithms where each argument is each factor. If the operation on the inside of a logarithm is division, we can rewrite it as subtraction of the numerator and the denominator in 2 individual logarithms. Our last log law is a way to rewrite exponentiation inside of a logarithm. If the argument is some sort of number raised to a power, we can rewrite it like this. What we've done here is brought this power that was on the x as a multiplier in front of the log. These might look a little bit weird, but they are actually related to our exponential rules. We had these rules. While these look a little bit different, these set of rules are actually saying very, very similar things. When you remember that the logarithm really represents the power that you need to put on a base in order to get something, we see that our rules are telling us that if we're multiplying things with powers, we can actually add the powers. If we're dividing things with powers, we can actually subtract the powers. We will use these laws of logarithms in both directions. Sometimes we'll take things that are multiplying or dividing or exponentiating and rewrite them as 2 separate logarithms. Sometimes we will take 2 separate logarithms that might be added or subtracted or maybe multiplied by a number and rewrite them as 1 logarithm. The laws of logarithms help us evaluate expressions like what we see in example 1. Each of these individually, I cannot really simplify and get to a nice rational number. Log base 6 of 2 does not simplify nicely because I can't raise 6 to some sort of power and get 2. There's not an integer or rational number that will do that. Similarly, I can't raise 6 to some sort of power and get 18. I can multiply it by a number and get 18, but I can't raise it to a rational power to get 18. But if we use our laws of logarithms, we might be able to combine this into 1 logarithm that can be simplified. I see here that I am adding between 2 different logarithms, and this makes me think about my first law of logarithms. If we use this first law up here and use it kind of backwards, 2 is taking the place of my x, and 18 is taking the place of my y. So I could write this as 1 single logarithm. When I do that, I'm going to keep the base the same. And I can write this with 1 argument, 2 times 18 on the inside. If I further reduce this, I can write this as log base 6 of 36. And now I wonder if I can evaluate this just using my definition of a logarithm. I need to know 6 to what power can get me 36? Well, I know that answer. That answer is 2. So by using the first law of logarithms to write this as 1 logarithm as opposed to the sum of 2 different logarithms, I can now evaluate this. Let's try a similar idea in B. Here I have the difference of 2 different logarithms with the same base. They are both log base 5 and I'm subtracting them. That makes me think of the second law of logarithms. Looks a lot like this piece here. So I can write this now as 1 logarithm with the same base, and I will divide the 2 arguments. I'll write it as 100 divided by 4. And now I know what 100 divided by 4 is. That is 25. So I can write this as log base 5 of 25, which now I can evaluate. I couldn't evaluate log base 5 of 100 or log base 5 of 4 and get a rational answer. I could put them in the calculator and get an irrational answer for each of those, but I couldn't get a rational answer. But now I know that this is going to be 2 because 5 squared is 25. 2 is the power that we have to put on 5 to get to 25. In part C here, we don't have the addition or subtraction of 2 different logarithms, but I am multiplying a logarithm by a number. And so I can use my third law of logarithms in the reverse direction, and I can bring that multiplier out in front to be an exponent on my argument. I would write it as log of 8 to the negative 1/3 power. Now, let's try to simplify the argument of my logarithm. 8 to the negative 1/3 power is the same thing as 1 over 8 to the 1/3 power. And 8 to the 1/3 power is the same thing as the cubed root of 8, which we know is 2. I can write this as the log of 1 over 2. I still can't evaluate this as an integer or rational answer. If I put log of 1/2, log base 10 of 1/2 into the calculator, I would get an irrational answer. But we do have a much simpler argument, and we no longer have multiplication in front. So this is a simplified version of the expression we started with. In example 2, we will use the laws of logarithms in the forward direction to expand an expression. In this way, we will turn a logarithm with a complicated argument into a series of several logarithms with simpler arguments. In this first part, we have an argument of 5x, and inside of that logarithm, 5 and x are being multiplied together. So I can use the first law of logarithms to write this as 2 logarithms and adding between. I'll keep the base of the logarithm the same, and the argument now, 5 in the first one and x in the second one. This is fully expanded because now 5 and x cannot be further broken down. In b, the argument of my logarithm is x to the 5th, y to the 7th. I have a couple of things going on here. I have multiplication of x's and y's to powers, and I have power on both x and y. I will first use the first law of logarithms to deal with the multiplication going on in here, because I can write this as multiplication with the factors x to the 5th and y to the 7th. So using the first law of logarithms, I can write log base 4 of x to the 5th plus log base 4 of y to the 7th. Now, my arguments, x to the 5th and y to the 7th, are things raised to powers. So I can use the third law of logarithms to bring that power out in front as a multiplier. When I do that, I will write 5 times log base 4 of x plus 7 times log base 4 of y. This is now fully expanded because x and y cannot be further broken down. And the last one, we have the natural logarithm of a pretty complicated argument. First, I will note that even though this is not written as log base a, we can still use our same law of logarithms for this, because remember, the natural logarithm is the same as log base e. The properties also will apply for our common logarithm, where we don't write the base at all. My argument, a to the 3rd times b all over the square root of c, has several operations going on together. I will first use my second law of logarithms because overall this is a fraction. I have a numerator and a denominator. So I can write this as the subtraction of 2 different natural logarithms, with the argument of the first being my numerator and the argument of the second being the denominator. To further expand, I will look at each logarithm individually. My first one, ln of a cubed times b, is a product, with a cubed being the first factor and b the second factor. So I can write this as the ln of a to the 3rd plus the ln of b using the first law of logarithms. I'm also going to look at this ln of square root of c, and because I know I have a rule about simplifying things with exponents on the inside, I'm going to switch notations, and instead of writing the square root of c, I'm going to write this as c to the 1/2 power. Remember that those are 2 different notations that mean the same thing. And in this case, it's really helpful to use that notation, because now in my next step, I can use my third law of logarithms to bring those powers out in front. I can bring this power of 1/2 as a multiplier in front of this natural logarithm, and I can bring this power of 3 in front of this natural logarithm. It'll look like this: 3 ln of a plus ln of b minus 1/2 ln of c, using the third law of logarithms. Finally, the laws of logarithms also allow us to write sums and differences of expressions of logarithms as one single logarithm. This is called combining logarithmic expressions. In the first one, we have 2 times ln of x plus the ln of y minus 1. The first thing that I notice here is that I have a 2 multiplying in front of that ln of x. I can use the third law of logarithms to write this as the ln of x squared plus the ln of y minus 1. Another thing that I notice is that I am adding two different logarithms. So I can use my first law of logarithms to write this as one single logarithm where I multiply the arguments. It'll look like this. We could choose to distribute the multiplication and write this as the ln of x squared times y minus x squared. It should be noted that we cannot use law of logarithms to do anything about the subtraction going on inside the argument of a logarithm. We do have a law of logarithm that pertains to subtraction, but it's the subtraction of two different logarithms, not the subtraction within an argument. So this is fully condensed, using both rules 3 and 1. Let's try to combine this last expression here, which is the sum and difference of three different logarithms, all with the same base. The first thing that I'll notice is that each of these have a multiplier in front. So I will first use my third law of logarithms to bring those multipliers up as exponents, writing it as log of r to the fifth plus log of s to the 1/2 minus log of r squared minus 1 to the fifth. I have to put this fifth power on my entire argument. Now, I notice that I am multiplying and dividing. We can use both the first and the second law of logarithms to fully reduce this. First, I will use the first law of logarithms to rewrite this part as log of r to the fifth times s to the 1/2. Now, I see that I'm subtracting two logarithms, so I can use the second law of logarithms to write this as division of the arguments in one single logarithm. Log of r to the fifth s to the 1/2 divided by r squared minus 1 to the fifth. I've now written this expression, which was originally the sum and difference of three different logarithms, as one logarithm.